Tonight, we're going to confront a question that most people assume has an obvious answer, but actually reveals one of the most sobering truths about our existence. Will we ever leave our solar system? I don't just mean sending a probe, or launch our cameras and sensors into space while we stay behind, but actually leave. Actually establish ourselves beyond the gravitational grip of our star, beyond the frozen edge of the Kuiper Belt, and beyond the boundary where the sun's influence fades into the darkness between stars. By the end of tonight, you're going to understand why this might be the most important limitation humanity has ever faced, and why the answer to this question isn't just about technology or time. It's about confronting the true scale of the cosmic prison we were born into. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what we've already accomplished, because it's actually more impressive than most people realize. We have left the solar system. Sort of. Both spacecraft were designed for a grand tour of the outer planets, a rare alignment that happens only once every 176 years. The planets were positioned in such a way that a spacecraft could use the gravity of each one to slingshot toward the next, gaining speed and changing direction without burning fuel. This alignment was first recognized by aerospace engineer Gary Flandreau in 1965 while he was a graduate student working at NASA's Jet Propulsion Laboratory. Flandreau realized that in the late 1970s, Jupiter, Saturn, Uranus, and Neptune would be arranged in an arc that would allow a spacecraft to visit all four in a single mission. This was an unprecedented opportunity. The last time the planets had been in a similar configuration was in the late 1780s, when Thomas Jefferson was serving as ambassador to France and the United States Constitution was being written. The next time it would happen would be in the 2150s, more than a century and a half in the future. NASA had to act fast. They proposed the Mariner Jupiter-Saturn project, which eventually became the Voyager program. The mission was supposed to last 5 years. Nobody expected both spacecraft to function for as long as they have. That was nearly 50 years ago. Systems have failed over the years. Some instruments have been shut down to conserve power, but the core systems are working. The spacecraft can still communicate with Earth. It can still transmit data. It's now over 15 billion miles from Earth, more than 160 times the distance from Earth to the Sun. To put that in perspective, when Voyager 1 sends a signal home, that signal, traveling at the speed of light, takes over 22 hours to reach us. That's how far away it is. The spacecraft is traveling at about 38,000 miles per hour relative to the Sun, which sounds fast, and it is fast by any human standard. You could travel from New York to Los Angeles in about 4 minutes at that speed. But it's barely moving, compared to the vast distances of space. It's been traveling at that speed for decades, and has barely scratched the surface of interstellar space. The Voyager missions transformed our understanding of the outer solar system. They discovered active volcanoes on Jupiter's moon Io, the first volcanoes ever found beyond Earth. They revealed the complex structure of Saturn's rings, showing thousands of individual ringlets and gaps, and discovered new moons orbiting both Jupiter and Saturn. Voyager 2 became the first, and still the only spacecraft, to visit Uranus and Neptune. It revealed Uranus's bizarre tilted magnetic field and discovered 10 new moons. At Neptune, it found active weather systems, including the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot, and discovered geysers of nitrogen erupting from Neptune's moon Triton. These discoveries rewrote textbooks. They showed us that the outer solar system was far more active, far more dynamic, far more interesting than anyone had imagined. And then both spacecraft kept going. They crossed the orbit of Pluto. Though Pluto was nowhere near their path, they entered the Kuiper Belt, the region beyond Neptune, filled with icy bodies and dwarf planets, and they kept transmitting data. In August 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind, that constant stream of charged particles flowing out from the sun, finally weakens and mingles with the interstellar medium. This was historic. For the first time, a human-made object had entered interstellar space, the region between stars. News articles proclaimed that Voyager had left the solar system. Scientists celebrated. It felt like a milestone, a crossing into new territory. But here's the thing that most people don't understand. Voyager 1 hasn't actually left the solar system. Not really. The heliopause isn't the edge of the solar system. It's just the edge of where the sun's wind dominates. The sun's gravitational influence extends much, much farther. The real edge of the solar system, the point where the sun's gravity finally loses its grip, is the outer boundary of the Oort cloud. The Oort cloud is a vast spherical shell of icy objects surrounding our solar system. It starts about 2,000 times the Earth-Sun distance and extends to about 100,000 times that distance. These are the leftover scraps from the solar system's formation, billions of comets drifting in the darkness, loosely bound to the sun's gravity. Occasionally, one gets nudged by a passing star's gravity and falls inward toward the sun, becoming a long-period comet that we see from Earth. The Oort cloud defines the true edge of the solar system. And Voyager 1, despite traveling for nearly 50 years, hasn't even reached the inner edge of the Oort cloud yet. It won't reach the inner edge for another 300 years. It won't completely exit the Oort cloud for another 30,000 years. Think about that. 30,000 years. Humans invented agriculture only about 12,000 years ago. The pyramids were built about 4,600 years ago. All of recorded human history, every civilization that has ever existed, every war fought, every discovery made, every person who has ever lived and died, all of it fits into a time span shorter than what it will take Voyager 1 to truly leave our solar system. And Voyager 1 is the fastest thing we've ever sent into deep space. We launched it with our most powerful rocket. We used gravity assists from multiple planets to accelerate it to speeds we can't currently achieve through propulsion alone. We did everything right. And it's still going to take 30,000 years to exit the solar system. This is the first hint of the problem. But before we go further, we need to be absolutely clear about what we're really asking. Voyager 1 is a machine. A remarkable machine, yes, packed with instruments and ingenuity, still functioning after nearly 50 years in the harshest environment imaginable. But it's just a machine. When we ask if we will ever leave the solar system, we're not really asking about machines. We're asking about us. Humans. Living, breathing people. Will humanity ever physically travel to another star? Will we ever establish ourselves beyond our sun's gravitational domain? Build colonies on planets orbiting other stars? Spread human civilization across multiple solar systems? That's a fundamentally different question than whether we can send a probe into interstellar space. We've already sent probes. Voyager 1 and 2 are out there right now. Pioneer 10 and 11 preceded them. New Horizons, after flying past Pluto, is also heading into interstellar space. We know how to build machines that can leave, but can we leave? Can humans, with our need for air and water and food, our vulnerability to radiation, our limited lifespans, our psychological need for variety and connection, can we actually make the journey to another star? And the honest answer, based on everything we currently understand about physics and the universe, might be no. Not because we lack imagination or courage, not because we haven't tried hard enough or invested enough resources, but because the universe is structured in a way that makes human interstellar travel almost impossibly difficult. Let me show you why. The solar system is much, much larger than most people realize, and the distances involved are so vast that our intuitions completely fail. When you see diagrams of the solar system in textbooks, they're helpful for showing what's out there, but they're completely wrong about scale. If you drew the solar system to scale with the planets at their actual sizes and distances, you'd need a football field just to show the inner planets, and Neptune would be over half a mile away. The Oort cloud would extend for thousands of miles in every direction. You couldn't fit it on any map or model. It would require a scale so large that the planets themselves would be invisible specks, smaller than grains of sand. But even the Oort cloud isn't the real challenge. The real challenge is what comes after. Once you leave the solar system, you're in interstellar space, the space between stars. And that space is empty in a way that's hard to comprehend. The nearest star to our Sun is Proxima Centauri, part of a triple star system called Alpha Centauri. It's 4.24 light-years away. A light-year is the distance light travels in 1 year. Light moves at about 186,000 miles per second, the fastest speed possible in the universe. In 1 year, light covers about 5.878 trillion miles. Proxima Centauri is 4.24 light-years away. That's about 24.9 trillion miles. Voyager 1, traveling at 38,000 miles per hour, would take about 73,000 years to reach Proxima Centauri. 73,000 years. That's not a journey. That's a geological epoch. That's longer than modern humans have existed as a species. Homo sapiens evolved about 300,000 years ago, but we only developed agriculture and settled civilizations about 12,000 years ago. 73,000 years ago, humans were still living in small nomadic groups, hunting and gathering, struggling to survive the last ice age. We hadn't invented writing. We hadn't built cities. We hadn't discovered mathematics or science or philosophy. And that's how long it would take our fastest spacecraft to reach the nearest star. Now, you might be thinking, okay, but Voyager 1 is old technology. We launched it in 1977 with 1970s technology. Surely we can do better now. We can. But not that much better. The fastest spacecraft we've ever built is the Parker Solar Probe, launched in 2018 to study the Sun. At its closest approach to the Sun, it reaches speeds of about 430,000 miles per hour. That's more than 10 times faster than Voyager 1. Sounds impressive. At that speed, how long would it take to reach Proxima Centauri? About 6,600 years. Still longer than all of recorded human history. Still far beyond any practical timescale for human exploration. And the Parker Solar Probe achieves that speed by falling toward the Sun, using the Sun's gravity to accelerate. It's not a speed we can maintain in interstellar space. Once you leave the solar system, there's nothing to pull you, nothing to accelerate against. You're coasting through empty space at whatever speed you manage to achieve while you are still near something massive. This brings us to the fundamental problem. Interstellar travel requires speeds we simply don't know how to achieve. To make a journey to another star in a human lifetime, you'd need to travel at a significant fraction of the speed of light. Let's say 10% of light speed. At that speed, it would take about 42 years to reach Proxima Centauri. That's long, but it's within a human lifetime. You could launch a mission with a crew in their 20s, and they'd arrive in their 60s. Difficult, but possible. The problem is getting to 10% of light speed. 10% of light speed is about 67 million miles per hour. To put that in perspective, that's about 156 times faster than the Parker Solar Probe at its maximum velocity. To accelerate a spacecraft to that speed requires an enormous amount of energy. The energy requirements scale with the square of the velocity. Doubling your speed requires 4 times the energy. Tripling your speed requires 9 times the energy. Going from our current maximum speeds to 10% of light speed requires increasing our velocity by more than 150 times. The energy required is astronomical. Let's do some math. The kinetic energy of a moving object is 1/2 times mass times velocity squared. Let's say we want to send a small spacecraft, maybe 1,000 kilograms, about the mass of a small car, to 10% of light speed. 10% of light speed is about 30 million meters per second. The kinetic energy would be 1/2 times 1,000 times 30 million squared. That's about 4.5 times 10 to the power of 17 joules. That's 450,000 trillion joules. For comparison, the total energy consumption of all humanity in a year is about 600,000 trillion joules. So to accelerate a 1,000 kilogram spacecraft to 10% of light speed would require about 3/4 of all the energy humanity uses in an entire year. And that's just for a tiny probe. If you want to send humans, you need a much larger spacecraft. You need life support, food, water, radiation shielding, living quarters, systems redundancy. A crewed interstellar spacecraft would probably mass at least 10,000 kilograms, more likely 100,000 kilograms or more. The energy requirements scale linearly with mass. A spacecraft 100 times more massive requires 100 times more energy. Now we're talking about 75 times the total annual energy consumption of human civilization just to accelerate the spacecraft. And that's not counting the energy needed to decelerate when you arrive, which is equally important unless you just want to fly past your destination at 67 million miles per hour. If you want to actually stop and explore, you need to decelerate, which requires just as much energy as accelerating in the first place. Now, you're looking at 150 times humanity's annual energy consumption. Where does that energy come from? Chemical rockets won't work. The best chemical rockets, like the hydrogen-oxygen engines used on the space shuttle, have exhaust velocities of about 2.8 miles per second. To reach 10% of light speed using a chemical rocket would require carrying so much fuel that the mass ratio, the ratio of initial mass to final mass, would be absurdly high. You'd need to carry thousands of times more fuel than payload. It's simply not feasible. Nuclear rockets are better. A nuclear thermal rocket, which heats propellant using a nuclear reactor, can achieve exhaust velocities of about 5.6 miles per second. The concept is straightforward. Instead of burning chemical fuel to create heat, you use a nuclear reactor. The reactor heats a propellant, typically liquid hydrogen, to extremely high temperatures. The hydrogen expands and shoots out the back of the rocket at high speed, creating thrust. Because nuclear reactions release far more energy than chemical reactions, you can heat the propellant to much higher temperatures and achieve higher exhaust velocities. The United States actually tested nuclear thermal rockets in the 1960s and early 70s under a program called NERVA, the Nuclear Engine for Rocket Vehicle Application. These tests were successful. The engines worked. They produced thrust. They demonstrated that nuclear thermal propulsion was feasible. But the program was cancelled in 1973 due to budget cuts and concerns about testing nuclear reactors. The Soviet Union also developed nuclear thermal rockets and even launched one into space in 1978. Though the mission ended when the reactor crashed back to Earth and scattered radioactive debris across northern Canada. Despite these early successes, nuclear thermal rockets have never been used for deep space missions. The technology works, but it's still not powerful enough for interstellar travel. 5.6 miles per second is impressive, about 60 times faster than a car on a highway, but it's only about 0.003% of the speed of light. At that speed, reaching Proxima Centauri would still take about 43,000 years. Better than chemical rockets, but still nowhere near good enough for interstellar travel. There's another type of nuclear rocket called a nuclear electric or ion drive. Instead of using the reactor to directly heat propellant, you use it to generate electricity, and then use that electricity to accelerate ions to very high speeds using electric fields. Ion drives can achieve exhaust velocities much higher than chemical or nuclear thermal rockets, up to 19 to 31 miles per second, sometimes even higher. The Dawn spacecraft, which explored the asteroids Vesta and Ceres, used ion propulsion powered by solar panels. It worked beautifully, allowing Dawn to orbit one body, leave, and then orbit another, something that would have been impossible with chemical propulsion. But ion drives produce very low thrust. The force they produce is tiny, measured in fractions of a newton. A newton is roughly the weight of an apple in your hand. Ion drives produce thrust equivalent to holding a few sheets of paper. This means acceleration is incredibly slow. It can take months or years to build up significant velocity. For interstellar missions, you'd need an ion drive powered by a massive nuclear reactor running continuously for decades just to reach a few percent of light speed. And you'd need to carry enormous amounts of propellant, even though ion drives are very efficient. The mass of the reactor, the ion drive system, the propellant, and the payload quickly becomes prohibitive. Ion drives, which use electric fields to accelerate ions to very high speeds, can achieve exhaust velocities of 19 to 31 miles per second. Much better, but they produce very low thrust. It would take years to accelerate a spacecraft to high speeds using an ion drive, and you'd still need an enormous power source to run the drive for that long. The best theoretical propulsion system we can imagine with current physics is a fusion rocket. Nuclear fusion, the process that powers the sun, releases enormous amounts of energy by combining light atomic nuclei into heavier ones. A fusion rocket could theoretically achieve exhaust velocities of up to 10% of light speed. This would make interstellar travel much more feasible because your exhaust velocity matches your target velocity. The problem is, we haven't figured out how to make fusion work yet, at least not in a controlled, sustained way that produces more energy than it consumes. We've been working on fusion energy for over 70 years. We've spent billions of dollars. We've built massive experimental reactors. And we're still not there. The latest experiments are showing promise, but we're still decades away from a working fusion power plant, let alone a fusion rocket small enough and efficient enough to propel a spacecraft. Even if we solve fusion, even if we build a working fusion rocket, we're still looking at journeys of decades to reach the nearest stars. There's one propulsion concept that could theoretically do better than fusion: antimatter. Antimatter is matter composed of antiparticles. Particles with the same mass as normal particles, but opposite charge. The antiparticle of an electron is a positron, identical to an electron except it has a positive charge instead of negative. The antiparticle of a proton is an antiproton, with a negative charge instead of positive. When matter and antimatter meet, they annihilate each other, converting 100% of their mass into energy, according to Einstein's famous equation, E equals mc squared. This is the most efficient energy release possible in the universe. Chemical reactions release energy by rearranging chemical bonds, converting a tiny fraction of the reactant's mass into energy. Nuclear fission releases about 0.1% of the fuel's mass as energy. Nuclear fusion releases about 0.7%. But matter, antimatter, annihilation converts 100% of the mass into energy. Nothing is more efficient. If you could build an antimatter rocket, you could theoretically achieve exhaust velocities approaching the speed of light. You could accelerate a spacecraft to 10, 20, even 50% of light speed. Interstellar travel would become practical. A journey to Proxima Centauri could take as little as 10 or 20 years. There's just one problem. We don't have any antimatter. Antimatter exists in nature. It's created in particle accelerators and in high-energy cosmic ray collisions. When a high-energy proton from space hits an atom in Earth's upper atmosphere, the collision can create particle-antiparticle pairs. These antiparticles exist for a fraction of a second before they encounter normal matter and annihilate. We can create antimatter in particle accelerators like the Large Hadron Collider at CERN. Physicists smash particles together at high energies and occasionally create antiparticles in the debris. But the quantities are minuscule. In a good year, CERN produces about 1/1,000,000,000 of a gram of antimatter. That's about 10 million trillion antiprotons, which sounds like a lot until you realize it's nowhere near enough for anything practical. To propel a spacecraft, you'd need kilograms of antimatter, possibly tons, depending on the mission profile. At current production rates, it would take billions of years to accumulate enough antimatter for a single interstellar mission. And that's not even considering the storage problem. Antimatter can't touch normal matter or it annihilates instantly. You can't put it in a regular container. You have to store it using magnetic fields, suspending the antimatter particles in a vacuum so they never touch the walls. This requires powerful magnets and constant energy input. If the power fails, the antimatter touches the container and explodes with the force of a nuclear bomb. The largest amount of antimatter ever stored at one time is about 100 billion antiprotons, held for about 16 minutes at CERN. That's about 0.0000001 grams. Nowhere close to what you'd need for a rocket. Antimatter rockets remain firmly in the realm of science fiction, at least for the foreseeable future. Maybe someday we'll figure out how to produce and store antimatter efficiently, but that day is not anywhere on the horizon. And that's just the propulsion problem. There are other challenges. Radiation. Interstellar space is filled with cosmic rays, high-energy particles traveling at close to the speed of light. On Earth, We're protected by our atmosphere and magnetic field. In space, there's no protection. Cosmic rays can damage DNA, increase cancer risk, and cause radiation sickness. On a journey lasting decades, the cumulative radiation exposure would be lethal unless the spacecraft has heavy shielding. But shielding adds mass, which makes the spacecraft heavier, which requires more energy to accelerate, which makes the problem worse. Then there's the problem of hitting things. Even tiny particles become dangerous at high speeds. And this is one of the most underappreciated challenges of interstellar travel. A grain of sand hitting a spacecraft, traveling at 10% of light speed, carries as much kinetic energy as an exploding hand grenade. Think about that. A single grain of sand, something so small you can barely see it, becomes a devastating projectile at relativistic speeds. The kinetic energy of a moving object is 1/2 times mass times velocity squared. Energy increases with the square of velocity. Double your speed, and you quadruple the kinetic energy of any collision. At 10% of light speed, even impacts with individual hydrogen atoms begin to be significant. Interstellar space isn't completely empty. It contains about 1 hydrogen atom per cubic centimeter on average. That doesn't sound like much, and it isn't. For comparison, the air you're breathing contains about 25 billion molecules per cubic centimeter. Interstellar space is a vacuum far better than anything we can create on Earth. But when you're moving at tens of thousands of miles per second, even that thin scattering of hydrogen atoms becomes a problem. Each atom you hit deposits its kinetic energy into your spacecraft. Most of that energy gets converted to heat. Your spacecraft's hull starts to heat up from the constant bombardment of atoms. At high enough speeds, this becomes significant. At 10% of light speed, the heating from interstellar hydrogen could raise the temperature of your spacecraft's front surface to hundreds of degrees. You'd need cooling systems, heat shields, materials that can withstand constant thermal stress. Then there are larger particles. Interstellar space contains dust grains, tiny specks of matter ranging from micrometers to millimeters in size. These are the remnants of dead stars, material blown off by stellar winds or ejected in supernova explosions. They drift through space, occasionally forming clouds where star formation occurs, but generally scattered thinly through the galaxy. The density of interstellar dust is extremely low. In the solar neighborhood, there's maybe 1 dust grain per cubic mile. That's incredibly sparse. You could travel through interstellar space for weeks or months without hitting a single grain. But on a journey lasting years or decades, the probabilities start to add up, and when you do hit one at relativistic speeds, the result is catastrophic. A dust grain 1 millimeter across, about the size of a pinhead, weighing about 1 microgram, 1/1,000,000th of a gram, hitting a spacecraft at 10% of light speed, releases about 45 megajoules of energy. That's equivalent to about 10 kilograms of TNT. That's a serious explosion, enough to punch a hole through any ordinary material, enough to potentially cripple or destroy your spacecraft. Some proposals for interstellar spacecraft include massive shields at the front, thick layers of material designed to absorb impacts. The Daedalus study, a theoretical interstellar probe design from the 1970s, proposed a shield made of beryllium, 50 tons of metal positioned ahead of the spacecraft to take the brunt of impacts. As the shield got hit by particles, material would ablate away, but the shield would protect the spacecraft behind it. By the time the ship reached its destination, most of the shield would be gone, eroded away by countless impacts. Other designs propose using magnetic fields to deflect charged particles. Since the interstellar medium is mostly ionized, consisting of protons and electrons rather than neutral atoms, a strong magnetic field could potentially push these particles aside before they hit the ship. The concept is similar to Earth's magnetosphere, which deflects the solar wind and protects us from radiation. A spacecraft could generate its own artificial magnetosphere, a bubble of magnetic force surrounding it. Charged particles entering this bubble would be deflected around the ship rather than hitting it head-on. But this requires powerful magnets and a lot of energy to maintain. And it doesn't help with neutral particles, dust grains that aren't electrically charged. Those would pass right through the magnetic field and hit the ship. You'd still need physical shielding. The interstellar medium isn't uniform. Some regions are denser than others. Molecular clouds, regions where hydrogen exists in molecular form rather than atomic form, can be hundreds of times denser than average interstellar space. If your trajectory takes you through a molecular cloud, the impact rate goes up dramatically. What was a manageable trickle of particles becomes a storm. Your shields would erode faster. Heating would intensify. The risk of a catastrophic impact with a larger grain increases. Ideally, you'd want to plot a course that avoids dense regions, sticking to the thinnest parts of the interstellar medium. But that might not always be possible. Space is three-dimensional. The path from our sun to another star is a straight line through three-dimensional space, and that line goes wherever it goes. If there's a molecular cloud in the way, you either go through it or you take a longer path around it, which means more time, more energy, more mass for life support and propellant. Navigation through interstellar space is far more complex than navigation through the solar system. Then, there's navigation. Traveling for decades, across trillions of miles, requires incredible precision. A tiny error in your trajectory at the beginning of the journey compounds over time and distance. You could end up missing your target star system entirely. You'd need constant course corrections, but that requires fuel, which adds mass. You'd also need to know exactly where you're going. Stars move. Proxima Centauri is moving relative to the Sun at about 15.5 miles per second. Over the decades of a journey, it will have moved a significant distance from where it was when you launched. You need to aim not at where the star is now, but at where it will be when you arrive. This is like trying to hit a moving target from thousands of miles away. Except the target is moving at tens of thousands of miles per hour, and you won't know if you aimed correctly until you arrive decades later. And then there's the psychological challenge. Imagine being sealed inside a spacecraft for 40 years. You leave Earth in your 20s. You arrive at your destination in your 60s, if you live that long. You never feel the wind on your face again. You never see a sunset, or a tree, or an ocean. You never meet anyone new. You're confined to a small metal box with the same handful of people for the rest of your life. Every day is the same. The same corridors, the same rooms, the same faces. And there's no going back. Even if you wanted to return to Earth, it would take another 40 years. By the time you got back, you'd be over 100 years old, and 80 years would have passed on Earth. Everyone you knew would be dead. The world would have changed beyond recognition. You'd be a relic from the past, more out of place than someone from the 1800s waking up today. Some have proposed multi-generational ships to solve this problem. The concept of a generation ship, also called a world ship or an ark, is straightforward in principle, but staggering in its implications. Instead of trying to complete an interstellar journey in one lifetime, you build a massive spacecraft, a miniature world capable of supporting hundreds or thousands of people for multiple generations. The people who launch don't expect to reach the destination. Neither do their children, nor their grandchildren. The journey might span 10, 20, or even 50 generations before the ship arrives at its target star. The people who finally land on a planet around another star will be the distant descendants of those who launched. People who were born on the ship, raised on the ship, lived their entire lives in space without ever setting foot on a planet. Generation ships have been a staple of science fiction for decades. Arthur C. Clarke explored the idea in Rendezvous with Rama. Kim Stanley Robinson examined it in Aurora. The concept is compelling because it seems to solve the problem of time. If the journey takes 300 years and humans live about 80 years, you need about 4 generations. The first generation launches. The second generation is born on the ship and grows up there. The third generation knows Earth only from history and stories. The fourth generation arrives at the destination, completes the mission, and establishes a colony on a new world. But when you think deeply about what a generation ship would actually entail, profound questions emerge. First, the ship itself would have to be enormous. You need living space for potentially thousands of people. You need food production, water recycling, air regeneration. You need energy systems that can run for centuries without resupply. You need manufacturing capability to repair and replace components that wear out. You need hospitals, schools, recreation areas. You need to create a complete, self-sufficient, closed ecosystem capable of lasting for hundreds of years. The largest spacecraft we've ever built, the International Space Station, masses about 420 metric tons and supports a crew of 6 people. A generation ship would need to be thousands or tens of thousands of times more massive. Some designs propose rotating cylinders to create artificial gravity through centrifugal force. The O'Neill cylinder concept, proposed by physicist Gerard K. O'Neill, in the 1970s, describes enormous rotating habitats, cylinders 20 miles long and 4 miles in diameter. Such a structure could house millions of people and would rotate once every 2 minutes to create Earth-like gravity on the inner surface. But building something on this scale in orbit around Earth would require resources and manufacturing capabilities far beyond anything we currently possess. You'd need to mine asteroids for metals, process millions of tons of material, assemble components in space. It would be the largest engineering project in human history. And that's just building the ship. Then you have to propel it. A ship massing millions of tons needs enormous amounts of energy to accelerate to even a fraction of light speed. The energy requirements are mind-boggling. Some designs propose using nuclear pulse propulsion, the Orion drive concept. You detonate nuclear bombs behind the ship, thousands of them in sequence, each explosion pushing the ship forward. It sounds insane, and it is, but the physics actually works. Project Orion was a real study conducted in the 1950s and 60s. Engineers calculated that you could accelerate a large spacecraft to about 10% of light speed using atomic bombs as propulsion. The ship would need a massive pusher plate, a shock absorber to smooth out the impulses from each explosion, and would need to carry thousands of nuclear devices. But it could work. Then, there are the social and psychological challenges. A generation ship is essentially a small, isolated society traveling through space for hundreds of years. How do you maintain social cohesion over that time? How do you prevent conflicts from escalating? On Earth, if a community has problems, people can leave, move to another town or country. On a generation ship, there's nowhere to go. You're trapped with the same small population for your entire life. Disputes, feuds, and divisions have no release valve. How do you govern such a society? Do you have elections? A permanent ruling council? What if the government becomes corrupt or tyrannical? What if there's a rebellion? On Earth, governments can be overthrown, but a revolution on a generation ship could be catastrophic. Damage to critical systems during a conflict could doom everyone aboard. Then there's the question of mission continuity. The original crew, the people who volunteered to launch, believed in the mission. They were willing to sacrifice their chance to ever see the destination because they believed in the goal of reaching another star. But what about their children? The second generation didn't choose this mission. They were born into it. They had no say in the decision to spend their entire lives on a spacecraft heading to a star they'll never reach. Will they resent their parents for that decision? Will they feel that their lives were stolen from them? And what about the third, fourth, fifth generations? Each successive generation is further removed from Earth, further removed from the original mission's motivation. Will they care about completing the mission? What if, 3 generations in, the majority of people on board decide they don't want to continue? What if they vote to turn the ship around and go back to Earth? Or worse, what if they just stop maintaining the ship, stop caring about the mission, and let the whole endeavor collapse? Some have proposed strict social engineering, raising children with a deep sense of duty to the mission, creating cultural traditions and religions that center on completing the journey. But this raises ethical questions. Is it right to indoctrinate children, to limit their freedom, to choose their own path in life? And would it even work? History is full of examples of children rejecting their parents' values. You can't guarantee that future generations will maintain the beliefs and motivations of the first generation. There are also genetic concerns. A generation ship has a limited population, maybe a few thousand people at most. That's a small gene pool. Over multiple generations, inbreeding becomes a problem. Genetic diversity decreases. Harmful recessive genes become more common. The population's health could deteriorate. To prevent this, the ship would need careful genetic management. Marriages would need to be arranged to maintain genetic diversity. Or perhaps the ship would carry frozen genetic material, sperm and eggs from thousands of donors, allowing future generations to maintain diversity through artificial reproduction. But again, this raises ethical questions. Who decides who gets to reproduce with whom? What if people refuse to follow genetic management protocols? Do you enforce them? Then there's the problem of technology and knowledge preservation. A generation ship needs to function for hundreds of years. Components will wear out, systems will fail, and the crew needs to be able to repair and replace them. This means maintaining not just the physical hardware, but the knowledge of how to maintain it. Engineering manuals, technical documentation, training programs, all of this needs to be preserved and passed down through generations. What if critical knowledge is lost? What if a key system fails and nobody remembers how to fix it because the last person with that expertise died 30 years ago and didn't train a replacement? What if the younger generations become less technically educated, more focused on daily survival and social issues, and gradually lose the skills needed to maintain the ship? This is sometimes called the entropic loss problem. Over time, Without external input, knowledge can be lost, skills can degrade, and technology can become less understood. The people aboard the ship might end up treating their technology as magic, following maintenance procedures by rote without understanding why, unable to innovate or adapt when problems arise. There's also the psychological burden of living your entire life on a ship where nothing changes. On Earth, we have seasons, weather, natural landscapes that change over time. On a generation ship, every day is the same. The same corridors, the same rooms, the same artificial environment. You wake up, you do your work, you eat, you sleep, and tomorrow is exactly like today, for your entire life. Some generation ship designs include large park areas, forests and meadows grown inside the habitat to provide variety and a connection to nature. But these would still be limited, artificial approximations of Earth's biosphere. You could never climb a mountain, never swim in an ocean, never see a wild animal. Your entire world is the inside of the ship. The question of children is particularly troubling. On Earth, when people decide to have children, they're bringing a new person into a world full of possibilities. That child can grow up to be anything, go anywhere, pursue any career or life path they choose. But a child born on a generation ship has no such freedom. Their life is predetermined. They will live on the ship, they will work to maintain the ship, and they will die on the ship. Their children will do the same. Is it ethical to bring a child into such a limited existence? Some would argue no, that it's a form of imprisonment, condemning someone to a life they didn't choose. Others would argue that life, even limited life, is better than no life at all. And besides, aren't all of us born into circumstances we didn't choose? But there's a difference between being born on Earth, with all its possibilities, and being born on a ship, traveling through interstellar space with no possibility of ever doing anything except what the mission requires. These questions have no easy answers. And that's why generation ships, despite being technically more feasible than faster-than-light travel or suspended animation, remain a deeply troubling concept. They ask us to sacrifice not just our own lives, but the lives of our descendants, for a goal that might not even matter by the time it's achieved. There's also the problem of where you're going. Proxima Centauri is the nearest star, but it's a small, dim, red dwarf. It has at least 2 planets, one of which, Proxima Centauri b, orbits in the habitable zone where liquid water could exist. Sounds promising, but red dwarfs are violent stars. They produce powerful flares that blast their planets with radiation. Proxima Centauri has been observed producing flares that increase its brightness by orders of magnitude. Any life on Proxima Centauri b would need to deal with this intense radiation environment. The planet might not even have an atmosphere. Red dwarf flares can strip away a planet's atmosphere over time. And even if the planet is habitable, we don't know that for certain. We've never seen it up close. We've only detected it indirectly by observing the tiny wobble it causes in its star's motion, and later by measuring the slight dimming of Proxima Centauri's light when the planet passes in front of it. The radial velocity method, measuring the star's wobble, tells us the planet's minimum mass, about 1.27 times Earth's mass. The transit method, measuring the dimming, tells us the planet's size, about 1.17 times Earth's diameter. From these measurements, we can calculate the planet's density, which suggests it's a rocky world like Earth, rather than a gas giant like Jupiter. But that's about all we know for certain. We don't know what the planet's surface is like. We don't know if it has water, an atmosphere, a magnetic field. We don't even know for certain that it orbits in the habitable zone. Red dwarfs, like Proxima Centauri, are dim and cool. Their habitable zones, the orbital distances where a planet could have liquid water, are much closer to the star than Earth is to the Sun. Proxima Centauri b orbits about 4.7 million miles from its star, compared to Earth's 93 million miles from the Sun. That's about 20 times closer. At that distance, the planet is probably tidally locked, meaning one side always faces the star, while the other side faces away, just like how the Moon always shows the same face to Earth. This creates extreme temperature differences. The day side could be scorching hot, while the night side could be frozen solid. Any liquid water might exist only in a narrow twilight zone between the two extremes, assuming there's enough atmospheric circulation to distribute heat. But we don't know if Proxima Centauri b has an atmosphere. Red dwarf stars, especially young ones, produce powerful flares and intense stellar winds. These can strip away a planet's atmosphere over time, especially for planets orbiting close to the star. Proxima Centauri is known for violent flare activity. In March 2016, observations detected a flare that increased the star's brightness by a factor of 68 in just 10 seconds. The energy released was enormous, far more powerful than any solar flare we've observed from our Sun. If Proxima Centauri b was in the path of that flare, the planet would have been bathed in lethal radiation. Any atmosphere would have been blasted by high-energy particles. Surface water could have been broken down into hydrogen and oxygen, with the light hydrogen escaping to space. Over billions of years of such flares, Proxima Centauri b might have lost most or all of its atmosphere and become a barren rock. We simply don't know. Future telescopes, like the extremely large telescope currently being built in Chile, might be able to detect an atmosphere around Proxima Centauri b by analyzing the starlight passing through it during transits. The James Webb Space Telescope could potentially do this as well, though Proxima Centauri b doesn't transit from our perspective, making atmospheric detection more difficult. Even if Proxima Centauri b turns out to be uninhabitable, it's not our only option. There are other star systems within a few light years that might have planets worth exploring. Barnard's star, about 6 light years away, is another red dwarf that has at least one planet, Barnard's star b, discovered in 2018. This planet is larger than Earth, about 3.2 times Earth's mass, and orbits far from its star, well outside the habitable zone. Surface temperatures are estimated at around -170 degrees Celsius, -274 degrees Fahrenheit. It's a frozen world, unlikely to have liquid water on its surface. But it might have subsurface oceans heated by the planet's interior, similar to what we suspect exists beneath the ice of Jupiter's moon Europa. Luton's star, about 12.4 light-years away, has 2 known planets, Luton b and Luton c. Luton b orbits in the habitable zone and has a mass about 3 times Earth's. It could potentially have liquid water, though again, we know very little about its actual conditions. Tau Ceti, about 12 light-years away, is a star very similar to our Sun, a G-type main sequence star, only slightly smaller and cooler. It has at least 4 confirmed planets, possibly more. One of them, Tau Ceti e, orbits in or near the habitable zone. It's a super-Earth, about 4 times Earth's mass. If it has an atmosphere and liquid water, it could potentially support life. Tau Ceti has been a popular target for SETI, the search for extraterrestrial intelligence. because it's so similar to our Sun. If life developed in our solar system around a G-type star, maybe it developed around other G-type stars too. But Tau Ceti's planetary system has a problem. The star has 10 times more comets and asteroids than our solar system. This means its planets likely experience far more impacts. Tau Ceti E, if it exists in the habitable zone, might be bombarded by comets and asteroids constantly, making the surface a dangerous place for life to develop. Epsilon Eridani, about 10.5 light-years away, is a young star, less than 1 billion years old. It has at least one confirmed planet, Epsilon Eridani b, a massive planet orbiting far from the star. The system also has 2 asteroid belts and a debris disk, suggesting the system is still forming and evolving. Any rocky planets in the habitable zone would be young and geologically active, possibly experiencing intense bombardment from leftover planetesimals. These are our nearest neighbors, the stars within about 12 light-years, and the planets we've detected around them. Most are not particularly inviting. Many are too hot or too cold. Many orbit red dwarfs that bombard them with radiation. Some are in systems filled with debris that would make impacts frequent and potentially catastrophic. But finding a truly Earth-like planet, one with liquid water, a stable atmosphere, moderate temperatures, and protection from radiation, one that could genuinely support human colonization, that's rare. Current estimates suggest that only about 20 to 50% of stars have planets in their habitable zones. And of those, only a fraction will actually have the right conditions for life as we know it. Finding another Earth, a true twin of our home world, might require searching thousands of star systems. And the nearest such planet might be dozens or even hundreds of light-years away, far beyond anything we could reach with current or near-future technology. This brings up an important point that often gets lost in discussions of interstellar travel. We're not just facing the challenge of traveling to another star. We're facing the challenge of finding a star worth traveling to. If we commit to an interstellar mission, if we build a generation ship or a fusion-powered spacecraft, or send a fleet of starships to another system, we're making an enormous investment of resources, time, and human life. We need to know the destination is worth it. We can't afford to travel for decades or centuries, only to discover the planet we were targeting is uninhabitable. This means we need better detection methods. We need telescopes powerful enough to study exoplanets in detail, to determine whether they have atmospheres, what those atmospheres are made of, whether there's water vapor, oxygen, methane, or other biosignatures that might indicate life. We need to know, before we launch, whether the destination is worth the journey. Some researchers argue we should focus on targets around Sun-like stars, G-type stars, similar to our own Sun. These stars are stable, long-lived, and their habitable zones are farther out, reducing the risk of tidal locking and radiation exposure. But G-type stars are less common than red dwarfs. About 75% of stars in our galaxy are red dwarfs, compared to only about 7% that are G-type stars like the Sun. This means Sun-like stars with Earth-like planets are going to be, on average, farther away. The nearest Sun-like star is Alpha Centauri A, part of the Alpha Centauri triple system. Alpha Centauri A is slightly larger and brighter than the Sun. It has a companion star, Alpha Centauri B, slightly smaller and dimmer, and both orbit each other every 80 years. Proxima Centauri, the red dwarf we've been discussing, orbits the pair at a great distance. In 2016, astronomers discovered a planet around Proxima Centauri. But what about Alpha Centauri A and B? Do they have planets? For a long time, we weren't sure. The two stars orbit each other, which complicates planet formation. But recent observations have found evidence of a possible planet around Alpha Centauri A. The data is still preliminary, but, if confirmed, Alpha Centauri A could have a planet in or near its habitable zone. That would be an incredibly valuable discovery. A planet orbiting a sun-like star less than 4.4 light-years away. Such a planet would immediately become the prime target for any future interstellar mission. We dedicate our best telescopes to studying it, trying to determine if it has an atmosphere, water, any signs that it could support life. And if it looked promising, it would be the obvious destination for humanity's first attempt to reach another star. Imagine spending 40 years traveling to Proxima Centauri, only to discover that Proxima Centauri B is a barren, radiation-blasted rock with no atmosphere and no possibility of supporting life. That would be devastating. All that effort, all that time, all that energy, all those resources for nothing. This is why some people argue that we should wait. Wait for better technology. Wait until we have faster propulsion systems, better shielding, better life support. Wait until we have the ability to scan distant planets in detail and confirm they're habitable before we commit to a journey. But here's the paradox. If you're always waiting for better technology, you never leave. There will always be something better on the horizon. Always a new engine design, a new propulsion concept, a new discovery that promises to make the journey faster, or safer, or cheaper. If you wait 20 years for a better engine, someone 20 years from now will say, let's wait another 20 years for an even better engine, and so on, indefinitely. At some point, you have to commit, even if it means traveling with technology that will be obsolete by the time you arrive, even knowing that a better ship might overtake you. This is sometimes called the incessant obsolescence problem, and it's been discussed in detail by researchers thinking about interstellar missions. The scenario goes like this. Imagine it's the year 2100, and we've developed a propulsion system that can accelerate a spacecraft to 5% of light speed. A mission to Proxima Centauri would take about 85 years. We launched the mission with great fanfare. A crew of colonists, perhaps in suspended animation, heads toward our nearest neighbor. But technology doesn't stop advancing. By 2150, 50 years into the mission, we've developed a new propulsion system capable of reaching 10% of light speed. A new mission launched in 2150 would take only 42 years to reach Proxima Centauri. The math is simple. The first mission, launched in 2100, arrives in 2185. The second mission, launched in 2150, arrives in 2192. Wait, that's wrong. Let me recalculate. The first mission takes 85 years, arriving in 2185. The second mission takes 42 years, arriving in 2192. The first mission still arrives first, but only by 7 years. But what if technology advances even faster? By 2200, we've developed a propulsion system capable of 20% of light speed. A mission, launched in 2200, takes only 21 years, arriving in 2221. That mission arrives before the 2100 mission, beating it by decades. The original crew wakes up from suspended animation, approaches Proxima Centauri, and finds humans already there, descendants of the faster mission who built a colony years ago. how do you think they'd feel? They sacrificed everything, left Earth knowing they'd never return, spent 85 years in transit, only to discover they were obsolete before they even arrived. It's a psychologically devastating scenario. And it gets worse if you extend the logic. Why should anyone launch in 2200 if by 2250 we might have 30% light speed? Why launch in 2250 if by 2300 we might have warp drive or some other breakthrough? If you always wait for the next improvement, you never go. This creates a paradox. The rational strategy seems to be to wait, but if everyone waits indefinitely, no one ever makes the journey. Some have argued there's a critical threshold, a point at which the technology is good enough that launching makes sense, even knowing better technology is coming. Maybe that threshold is 10% of light speed. At that speed, trips to nearby stars take decades rather than millennia, making them feasible within a human or extended human lifespan. Once you cross that threshold, the benefits of waiting diminish. Yes, faster engines will be developed, but the difference between 42 years and 21 years, while significant, isn't as transformative as the difference between 4,000 years and 42 years. At some point, the technology is good enough, and the value of actually going outweighs the value of waiting for marginal improvements. But we're nowhere near that threshold yet. With current technology, interstellar missions take tens of thousands of years. Even with optimistic projections for fusion or light sail technology, we're looking at centuries or many decades. The incessant obsolescence problem is very real for us. Any mission we launch today would almost certainly be overtaken by a future mission using better technology. So perhaps the right strategy is to wait, to continue developing better propulsion, better life support, better everything, until we reach that critical threshold where launching makes sense. But how long will that take? 50 years? 100? 500? We don't know, and there's no guarantee we'll ever reach it. Maybe the laws of physics impose hard limits we can't overcome. Maybe 10% of light speed is impossible with any practical technology. If so, we might wait forever for a threshold that never comes. Some people have proposed sending information instead of people. Instead of trying to physically transport humans across interstellar distances, why not just send the information needed to recreate humans? Send a detailed genetic database, instructions for synthesizing human DNA, and plans for building artificial wombs and raising children. Launch a robotic spacecraft that travels to another star system, uses local resources to build the necessary infrastructure, and then creates humans from scratch when it arrives. This solves many problems. Robots don't need life support. They don't get bored or depressed. They don't suffer radiation damage the same way biological organisms do. They can be powered down for most of the journey to save energy. And information is light. You can store the entire human genome, all 3 billion base pairs, in less than a gigabyte of data. You could fit libraries of human knowledge on storage devices weighing a few kilograms. The spacecraft could be much smaller and lighter, requiring far less energy to accelerate. But this creates other questions. Are the humans created at the destination really us? They'd be genetically human, but they'd have no connection to Earth, no parents, no childhood, no cultural heritage. They'd be raised by robots on an alien world. Would they even consider themselves human? Would they care about Earth or humanity's legacy? And who decides which genetic information to send? Whose DNA gets included? How do you ensure genetic diversity? How do you avoid programming these future humans with our biases and limitations? It's a profound ethical minefield. There's another possibility that some consider. Maybe we never leave physically, but we send our consciousness. If we develop advanced artificial intelligence and the ability to upload human minds into digital form, we could send consciousness across the stars at the speed of light. Beam, a radio signal containing a human mind to another star system, where machines receive it, download it, and instantiate it in a new body or a virtual environment. The trip would take years. 4 years to Proxima Centauri at the speed of light. But that's nothing compared to the thousands of years required for physical travel. Of course, this assumes we can upload minds, which we don't know how to do. It assumes consciousness can exist in digital form, which is philosophically contentious. And it raises the question of identity. If a copy of your mind arrives at another star, is it you? Or is it a copy, while the original you remains on Earth? If the original you dies, does it matter that a copy exists elsewhere? These are questions that don't have easy answers. Despite all these challenges, despite the enormous distances, the energy requirements, the technological hurdles, and the philosophical questions, there are people seriously working on interstellar travel. Project Breakthrough Starshot, funded by Russian billionaire Yuri Milner and supported by physicist Stephen Hawking before his death, proposes sending tiny spacecraft to Alpha Centauri using light sails. The project was announced in April 2016 with initial funding of $100 million. The goal is ambitious but potentially achievable with technology that either exists or is within reach. A light sail is exactly what it sounds like. A large, thin, reflective sheet that catches photons from a laser beam and uses their momentum to accelerate. Photons, particles of light, have no mass, but they do have momentum, a consequence of quantum mechanics and special relativity. When a photon bounces off a reflective surface, it transfers twice its momentum to that surface, creating a tiny push. Individually, the push from a single photon is negligible, impossibly small. But if you have a powerful enough laser producing trillions upon trillions of photons per second, and a large enough sail to catch them, you can create significant acceleration. The advantage of light sail propulsion is that you don't have to carry your energy source with you. The laser stays on the ground, or in orbit around Earth. The spacecraft itself is just a sail and a tiny payload. No engines, no fuel tanks, no massive reactor. This allows it to be incredibly light. Breakthrough Starshot proposes spacecraft weighing about 1 gram each, roughly the mass of a paperclip. This isn't a spacecraft in the traditional sense. It's a star chip, a wafer containing cameras, sensors, navigation equipment, power supply, and a small laser for communication, all miniaturized to fit on a chip a few centimeters across. Attached to this chip is a light sail, a square sheet of reflective material, about 4 meters on each side, incredibly thin, just a few hundred atoms thick. The total mass of the star chip and sail together is about 1 gram. To accelerate these star chips, Breakthrough Starshot proposes building a massive laser array on Earth, possibly in the Atacama Desert in Chile, or another high-altitude location with clear skies. This array would consist of thousands of individual lasers working together, combining their beams into a single focused point. The total power output would be about 100 gigawatts, 100 billion watts. That's enormous. For comparison, a large nuclear power plant produces about 1 gigawatt. This laser array would produce the power of 100 nuclear plants, but only in brief pulses. The array would fire for about 10 minutes at each star chip, accelerating it from rest to about 20% of the speed of light. 20% of light speed is about 37,000 miles per second, or about 134 million miles per hour. At that speed, the star chip would cross the distance to Proxima Centauri in about 20 years. Add another 4.24 years for the light carrying its data to travel back to Earth, and you get a total mission time of about 24 years from launch to receiving results. That's within a human lifetime. Someone working on the project today could launch the mission and live to see the results. This is what makes Breakthrough Starshot so compelling. It's not a multi-generational mission. It's not something where the people who start it will never see it completed. It's a project that could potentially be completed within the careers of the people working on it. But the technical challenges are immense. First, there's the laser array. Building a 100 gigawatt laser system is no small feat. The cost would be in the billions of dollars. The engineering challenges are significant. You need thousands of lasers, perfectly synchronized, their beams combined with exquisite precision. Any misalignment and the beam spreads out, reducing the force on the sail. The lasers need to track the star chip as it accelerates away from Earth. During the 10-minute acceleration phase, the star chip is accelerating at about 60,000 Gs, 60,000 times Earth's gravity. It's moving faster and faster, receding from Earth at an ever-increasing rate. The laser beam needs to follow it, adjusting constantly to keep the beam focused on the tiny 4-meter sail. This requires incredibly precise pointing and tracking systems. Then there's the problem of the atmosphere. The laser beam has to pass through Earth's atmosphere to reach the star chip. The atmosphere absorbs and scatters light. Turbulence in the air causes the beam to spread and wander. This is the same phenomenon that makes stars twinkle, atmospheric turbulence, bending and distorting starlight. For a ground-based laser, this is a serious problem. The proposed solution is adaptive optics, systems that measure atmospheric turbulence in real time and adjust the laser beam to compensate. Ground-based telescopes use similar systems to sharpen images of distant objects. But applying this to a laser beam, accelerating a spacecraft, is more challenging. The sail itself must be incredibly precise. It needs to be perfectly flat and perfectly reflective. Any wrinkles, any imperfections, and the light pressure won't be uniform across the sail. The star chip will start to tumble or veer off course. Controlling the sail's orientation during acceleration is critical. Small adjustments in the sail's angle can be used to steer, but this requires active control systems, sensors to detect orientation, and mechanisms to adjust the sail. All of this has to fit within the 1-gram mass budget. Then, there's the interstellar journey itself. Once the laser turns off, after 10 minutes of acceleration, the star chip is on its own. It's coasting through space at 20% of light speed, heading toward Proxima Centauri. The journey takes 20 years. During that time, the star chip is bombarded by cosmic rays, high-energy particles that can damage its electronics. It's passing through the interstellar medium at relativistic speeds. Even though the interstellar medium is incredibly thin, at these speeds, collisions with hydrogen atoms and dust grains become significant. A 1-gram spacecraft has very little shielding. A single dust grain impact could destroy it. The probability of hitting a destructive dust grain during the 20-year journey is estimated at a few percent per mission. Not terrible, but not great either. The proposed solution is to launch not one starship, but thousands of them. Send an entire fleet. If a few percent are destroyed by dust impacts, the rest will get through. You only need one to succeed to get data back. When the starship arrives at Proxima Centauri, it has minutes, maybe hours, to gather data as it flies past at 20% of light speed. It can't slow down. There's no way to decelerate. The laser that accelerated it is back at Earth, 4.2 light-years away. So it's a flyby mission. The starship snaps photographs, takes measurements, records everything it can in the brief time it's within range of Proxima Centauri and its planets. Then it uses its onboard laser to beam the data back to Earth. The laser is tiny, maybe a milliwatt or less. The beam spreads out over the 4.2 light-year distance. By the time it reaches Earth, the signal is incredibly weak. We'd need enormous receivers, telescopes with collecting areas measured in square miles to detect the signal. The entire data transmission might take days or weeks, sending back images and measurements one bit at a time. And all of this, the laser array, the starships, the receivers, the project management, the tracking and coordination, needs to work perfectly for a mission that takes over 20 years and costs billions of dollars. One mistake, one failure, and a starship is lost. But if it succeeds, the payoff is extraordinary. We'd have close-up images of another star system. We'd see Proxima Centauri's planets with resolution comparable to what we can achieve for planets in our own solar system. We'd learn whether Proxima Centauri b has an atmosphere, whether it has water, whether it shows any signs of life. We'd be seeing another world up close for the first time in human history. Breakthrough Starshot is still in early development. They're testing materials for the sails. They're working on miniaturizing electronics. They're exploring laser technologies. But the project is progressing. If funding continues and technical challenges are overcome, we might see the first launch attempts in the 2030s or 2040s. And if those succeed, we'd start receiving data back in the 2050s or 2060s. That's within the lifetime of people alive today. But remember what we established at the beginning. Breakthrough Starshot, as revolutionary as it would be, is still sending machines, not humans. Tiny 1-gram robots traveling one way, never coming back, never experiencing the journey, never walking on another world. It would give us incredible data, yes. It would be a monumental achievement. But it wouldn't be us leaving the solar system. And that's the distinction that matters. The question isn't whether we can send information or machines across interstellar space. The question is whether humans, with all our biological limitations and needs, can make that journey. And based on everything we've discussed, the propulsion challenges, the energy requirements, the radiation, the micrometeorites, the navigation, the psychology, the answer remains deeply uncertain. We are, in a very real sense, trapped, not because we lack the will or the curiosity, but because the universe is structured in a way that makes it extraordinarily difficult. The speed of light is the ultimate speed limit. Nothing with mass can reach it. Even approaching it requires ridiculous amounts of energy. And the distances between stars are measured in light years, distances so vast that even traveling at close to light speed would take years or decades. We're trapped by geometry. The universe is expanding. Space itself is stretching. Distant galaxies are moving away from us faster than light, not because they're traveling through space faster than light, but because the space between us and them is expanding. Those galaxies are forever beyond our reach. we will never travel to them, no matter how advanced our technology becomes. Even stars in our own galaxy are separated by such enormous distances that reaching them represents a challenge we may never overcome. Our solar system is our home, possibly our permanent home. And it's vast, far larger and more resource-rich than most people realize. The sun provides energy, enormous amounts of it, about 3.8 times 10 to the power of 26 watts, radiating out into space. Earth captures only about 1/1000th of that energy, a tiny fraction. The rest flows past us into empty space. If we could capture even a small percentage of the sun's total output, we'd have more energy than human civilization could use for millions of years. Concepts like Dyson swarms, proposed by physicist Freeman Dyson in 1960, imagine surrounding the sun with a massive shell or swarm of solar collectors, capturing a significant portion of its energy output. Building such a structure would require mining asteroids, processing raw materials in space, and assembling millions of individual collectors in solar orbit. It would take centuries, but the energy payoff would be extraordinary. The planets and asteroids provide resources, more raw materials than we could ever exhaust. The asteroid belt, located between Mars and Jupiter, contains millions of asteroids ranging in size from dust particles to Ceres, a dwarf planet 588 miles in diameter. The total mass of the asteroid belt is estimated at about 3% of the Moon's mass, which might not sound like much, but it's still an enormous amount of material. And unlike the Moon, which is mostly rock, asteroids are diverse. Some are metallic, composed primarily of iron and nickel. Others are carbonaceous, rich in water and organic compounds. Still others are silicate rocks, similar to Earth's crust. A single metallic asteroid, 16 Psyche, a 140-mile diameter body, is estimated to contain $10 quintillion worth of iron, nickel, and other metals at current market prices. Of course, if you brought that much material back to Earth, you'd crash the metals market instantly. But the point isn't to bring it back. The point is that there are resources out there in space, resources that could be used to build habitats, spacecraft, solar collectors, whatever we need. Mars could be terraformed, transformed over centuries into a world more Earth-like. The process would be slow and difficult, requiring technologies we're still developing. You'd need to warm the planet, thicken its atmosphere, and introduce water. One proposal involves releasing the carbon dioxide locked in Mars's polar ice caps and in the soil. Carbon dioxide is a greenhouse gas. If you release enough of it, the planet warms up. As it warms, more carbon dioxide sublimates from the ice, creating a runaway greenhouse effect that continues warming the planet. Eventually, temperatures might rise enough for liquid water to exist on the surface. You could then introduce bacteria and plants engineered to survive in Martian conditions, organisms that would slowly convert carbon dioxide into oxygen over thousands of years. Eventually, Mars might have a breathable atmosphere, though it would take a very long time, possibly tens of thousands of years. But it's theoretically possible. Mars has a 24.6-hour day, close to Earth's. It has seasons, polar ice caps, mountains, valleys, and evidence of ancient rivers. In many ways, Mars is the most Earth-like planet we've found. It would be a harsh world compared to Earth, colder, with lower gravity and less atmosphere, but it could potentially become a second home for humanity. Jupiter's moon Europa is one of the most intriguing targets for exploration. Beneath its icy crust, about 6 to 9 miles thick, lies a global ocean estimated to be about 62 miles deep. That ocean contains more liquid water than all of Earth's oceans combined. It's kept liquid by tidal heating, the gravitational interaction between Europa, Jupiter, and the other Galilean moons. As Europa orbits Jupiter, its orbit is slightly elliptical, causing the moon to flex and stretch. This flexing generates heat in Europa's interior, enough to keep the subsurface ocean liquid despite the moon's distance from the sun. Where there's liquid water and energy, there might be life. Europa's ocean is in contact with a rocky seafloor, allowing chemical reactions between water and rock, reactions that could provide nutrients and energy for life. On Earth, deep ocean hydrothermal vents support entire ecosystems based on chemosynthesis rather than photosynthesis, organisms that derive energy from chemicals rather than sunlight. Europa might have similar ecosystems in its dark ocean depths. Future missions are being planned to study Europa in detail, to send spacecraft that could land on the ice, drill through it, and deploy submersibles to explore the ocean beneath. Finding life on Europa, even microbial life, would be one of the most profound discoveries in history. It would prove that life can arise independently in multiple places, that we're not alone, that the universe might be full of life. Saturn's moon Enceladus is another icy world with a subsurface ocean. It's much smaller than Europa, only about 310 miles in diameter, about the size of Arizona. But in 2005, the Cassini spacecraft discovered geysers erupting from cracks near Enceladus's south pole, plumes of water vapor, ice particles, and organic molecules shooting out into space. These plumes come from the subsurface ocean. They spray material directly into space, where spacecraft can sample it without even landing. Cassini flew through these plumes multiple times, analyzing their composition. The measurements revealed water, carbon dioxide, methane, ammonia, and simple organic molecules, the building blocks of life. The ocean on Enceladus is in contact with a rocky core, and there's evidence of hydrothermal activity, warm water reacting with rock at the ocean floor. All the ingredients for life are present: water, organic molecules, energy, and a stable environment. If life exists on Enceladus, it could be detected by sending a mission to fly through the plumes and analyze them in detail, looking for biological molecules or other signs of life. Saturn's largest moon, Titan, is another fascinating world. It's the only moon in the solar system with a thick atmosphere, thicker than Earth's, composed mostly of nitrogen, with traces of methane and other hydrocarbons. The surface pressure is about 1.5 times Earth's sea level pressure. Titan is cold, minus 179 degrees Celsius, minus 290 degrees Fahrenheit, far too cold for liquid water. But it has lakes and seas of liquid methane and ethane, vast bodies of hydrocarbons that cycle through Titan's atmosphere, much like water cycles on Earth. It rains methane on Titan, carving river channels and filling lakes. The Dragonfly mission, a nuclear-powered rotorcraft scheduled to launch in 2028 and arrive at Titan in 2034, will explore this alien world, flying from site to site, analyzing the chemistry, searching for prebiotic molecules, or even life based on entirely different chemistry than Earth's. The outer solar system is full of moons, many of them potentially harboring subsurface oceans. Jupiter's moon, Ganymede, the largest moon in the solar system, likely has a subsurface ocean beneath a thick ice shell. Jupiter's moon, Callisto, might as well. Even distant Neptune's moon, Triton, captured from the Kuiper Belt, and forced into a retrograde orbit, shows signs of past or present geological activity and might have liquid water beneath its surface. Each of these worlds is a potential destination for human exploration and possibly even colonization, though not in the traditional sense of living on the surface. More likely, we'd build habitats in orbit or beneath the ice, protected from radiation and the harsh surface conditions. And then there are the Lagrange points, locations in space where the gravitational forces of two large bodies, like the Earth and Moon, or the Earth and Sun, balance out, creating stable positions where objects can remain without expending fuel. The Earth-Moon system has 5 Lagrange points. The Earth-Sun system has 5 as well. These points could host space stations, massive rotating habitats, housing thousands or millions of people, living in artificial gravity, shielded from radiation, sustained by resources mined from asteroids and the Moon. The concept of space habitats goes back to the 1970s with Gerard K. O'Neill's work. O'Neill proposed building cylindrical colonies, rotating to create artificial gravity, with land area inside the cylinder where people could live. These habitats would be entirely self-sufficient, recycling air and water, growing food in enclosed farms, powered by solar energy. Each habitat could house tens of thousands of people. You could build thousands of them throughout the solar system, far more living space than exists on Earth's surface. Jeff Bezos, founder of Amazon and Blue Origin, has championed this vision, arguing that the solar system could eventually support 1 trillion humans living in space habitats. Earth would become a nature preserve, a protected world where most of the surface is wilderness, while the bulk of humanity lives in orbit, in habitats customized to different preferences, some with higher or lower gravity, some with different day lengths or climates. All of this is possible without ever leaving the solar system. The solar system contains everything we need: energy from the sun, raw materials from asteroids and moons, space to expand into for millions of years. We could build a thriving spacefaring civilization, explore dozens of worlds, make discoveries that rival anything we might find around other stars, all without needing to cross the vast gulfs between stars. Maybe we don't need to travel to other stars. Maybe the solar system is our island, and we should focus on making the most of what we have here rather than chasing an impossible dream. But humans are explorers. We've always pushed boundaries, always ventured into the unknown. When our ancestors left Africa tens of thousands of years ago, they didn't know what was out there. They didn't know if they'd find food or shelter or other people. They went anyway. When Europeans sailed across the Atlantic in the 15th and 16th centuries, they didn't know what was on the other side. The voyages were dangerous. Many ships were lost. Many sailors died. They went anyway. When we launched the Apollo missions to the Moon, we didn't know for certain we'd succeed. The rockets were experimental. The computers were primitive by today's standards. The astronauts knew they might not come back. They went anyway. There's something in human nature that compels us to explore, to see what's over the next hill, across the next ocean, beyond the next horizon. And for us today, the next horizon is the stars. We can see them. We can study them with telescopes. We can detect planets orbiting them. We can analyze their light and learn about their composition. But we can't go there. Not yet. Maybe not ever. Unless something changes. Unless we discover new physics, new principles that allow us to circumvent the limitations we currently face. Science fiction has proposed many solutions. Warp drives that bend space around a spacecraft, allowing it to move faster than light without actually traveling faster than light. Wormholes, shortcuts through space-time that connect distant points in space. Hyperspace, an alternate dimension where the normal rules of physics don't apply. These ideas are fun to think about, and some are even based on real physics. Einstein's general relativity does allow for solutions where space is warped, in ways that could theoretically enable faster-than-light travel. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a space-time geometry where a bubble of space contracts in front of a spacecraft and expands behind it, allowing the spacecraft to move faster than light from the perspective of an outside observer while remaining stationary within its own bubble. It's a mathematically valid solution to Einstein's equations. But it requires exotic matter with negative energy density, which we've never observed and don't know how to create. It might not even be possible. Wormholes, tunnels through space-time connecting distant points, also appear in general relativity. But they're unstable. They collapse almost instantly unless held open by exotic matter. Again, something we don't know how to make. And even if we could create a stable wormhole, we don't know how to control where it goes or how to travel through it safely. These ideas remain firmly in the realm of speculation. They're not impossible, according to the laws of physics as we currently understand them, but they require things we've never observed and don't know how to produce. Betting on them would be like ancient humans, betting that someday they'd discover a way to fly by flapping their arms really fast. Technically, the physics doesn't forbid it, but it's not how flight actually works. Maybe there's a way to leave the solar system and travel to other stars that we haven't thought of yet. Maybe future discoveries will open doors we can't currently imagine. But based on what we know now, the answer to the question, will we ever leave our solar system, is uncertain at best. We've sent probes into interstellar space. We might send more sophisticated probes to nearby stars within the next century. But sending humans, establishing a physical presence beyond the solar system, that's a challenge we may never overcome. Not because we're not smart enough, or brave enough, or determined enough, but because the universe is structured in a way that makes it extraordinarily difficult. The stars are far away, almost unimaginably far. The energy required to reach them is enormous. The time required is longer than human civilizations last. We are, in a very real sense, trapped by the speed of light. Trapped by the vast emptiness between stars. Trapped in our solar system. And maybe we need to accept that. Maybe we need to shift our perspective and realize that the solar system, as vast and rich as it is our home. And we should focus our efforts on exploring and utilizing what's here rather than mourning what we can't reach. There are 8 planets, hundreds of moons, millions of asteroids, billions of comets. There are resources beyond anything we've ever accessed on Earth. There's room for billions of people to live and thrive without crowding. There are mysteries to solve, discoveries to make, wonders to explore, all within our solar system. We could spend the next million years exploring just what's here and never run out of new things to learn. But there's also something profound about the isolation, about being trapped in our solar system, unable to reach the stars. It forces us to confront a question that has haunted astronomers and philosophers since we first understood how vast the universe is. Where is everybody? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked this question during a lunch conversation in 1950. The logic is straightforward. The universe is about 13.8 billion years old. Our galaxy alone contains hundreds of billions of stars. Many of those stars have planets. Current estimates suggest there might be tens of billions of Earth-like planets in our galaxy alone. If even a tiny fraction of those planets developed life, and an even tinier fraction of those developed intelligent life, there should be thousands or millions of technological civilizations in the Milky Way. Some of those civilizations would be much older than ours. The Sun is only about 4.6 billion years old, relatively young compared to many stars in the galaxy. Stars formed billions of years before our Sun. Planets around those stars could have developed life billions of years before Earth. A civilization that got a billion-year head start on us would have technology so advanced we couldn't even comprehend it. They would have had ample time to spread throughout the galaxy, colonizing countless star systems, building megastructures, sending out signals we could detect. So where are they? Why haven't we seen any evidence of alien civilizations? Why is the sky silent? This is the Fermi paradox. Many explanations have been proposed. Maybe intelligent life is incredibly rare. Maybe the jump from simple life to complex life is harder than we think. Earth had simple, single-celled life for over 3 billion years before complex multicellular organisms evolved. Maybe that transition is so difficult, so unlikely, that it only happens once in a billion planets. Maybe intelligence itself is rare. Life on Earth has existed for almost 4 billion years. But intelligence, technological intelligence, capable of building radios and spacecraft, has only existed for a few thousand years. Maybe most planets with life never develop intelligence. Maybe dinosaurs would still rule Earth if an asteroid hadn't wiped them out 66 million years ago, and intelligence would never have evolved. Or maybe intelligence is common, but technological civilization is fragile. Maybe civilizations tend to destroy themselves shortly after developing advanced technology. Nuclear weapons, biological warfare, artificial intelligence, climate change, resource depletion, all of these pose existential risks. Maybe most civilizations don't survive long enough to become spacefaring. They reach a certain level of technology and then collapse, either through war, environmental catastrophe, or some other disaster. This is sometimes called the Great Filter Hypothesis. Somewhere between the origin of life and the development of galaxy-spanning civilizations, there's a filter, a step so difficult that almost no one makes it through. The question is, where is the filter? Is it behind us, somewhere in our past? Maybe the origin of life itself is the filter, or the evolution of complex cells, or the development of intelligence. If so, we've already passed the hardest part, and our future might be bright. Or is the filter ahead of us? Maybe technological civilizations inevitably destroy themselves, and we're heading toward that same fate. If every civilization collapses within a few centuries of developing nuclear weapons and fossil fuel-based industry, that would explain why we don't see evidence of advanced aliens. They existed briefly and then vanished, just like we might. Another possibility is that interstellar travel is simply too hard. Maybe we're not alone. Maybe there are millions of civilizations in the galaxy, but they're all trapped in their home solar systems, just like us, limited by the speed of light and the vast distances between stars. They can send radio signals, but those signals are weak and spread out over enormous volumes of space. Detecting them is like trying to hear a whisper from across an ocean during a storm. We've been listening for alien signals since 1960 with Project Ozma, the first SETI experiment. We've scanned thousands of stars at various frequencies, listening for patterns that might indicate intelligent transmission. We've heard nothing conclusive. A few strange signals over the years, like the WOW signal, detected in 1977, a strong narrowband radio signal that lasted 72 seconds and never repeated. It's never been explained, but it's also never been confirmed as extraterrestrial. Maybe aliens are out there broadcasting, but we're not listening at the right frequency or the right time or in the right direction. Space is vast. Radio signals weaken with distance. Even a powerful transmission from a civilization 100 light-years away might be too faint to detect by the time it reaches us. Or maybe they're not broadcasting at all. Maybe they're listening, just like we are, waiting for someone else to make the first move. Everyone staying quiet, afraid to reveal their presence. This is the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin. The idea is that the universe is like a dark forest. Every civilization is a hunter creeping through the trees, trying to survive. If you reveal your presence, you don't know what might come looking for you. Maybe other civilizations are hostile. Maybe the only safe strategy is to stay hidden, to listen but never broadcast. If everyone thinks this way, the galaxy could be full of civilizations, all hiding from each other, and we'd never know. It's a dark vision, but it's one possible explanation for the silence. Or maybe intelligence and civilization are common, but they're just not interested in us. Maybe we're being observed, studied, but not contacted. Maybe there's a galactic protocol, a rule that says you don't interfere with developing civilizations. You let them mature on their own. This is the zoo hypothesis. We're in a cosmic nature preserve, and the advanced aliens are watching us from a distance, waiting to see what we do. End, whether we destroy ourselves or manage to build a sustainable civilization. Only when we've proven ourselves worthy will they make contact. It sounds comforting. The idea that we're being watched over by benevolent elder civilizations, but there's no evidence for it. It's pure speculation. The simplest explanation might be the most sobering. Maybe we're alone. Maybe life is common, but intelligence is rare, vanishingly rare. Maybe Earth is the only planet in the observable universe where life has developed technology and consciousness. If so, we bear an enormous responsibility. We're not just responsible for our own survival. We're responsible for consciousness itself, for the universe's ability to understand itself. Every star, every galaxy, every quantum field exists, whether or not anyone is watching. But without consciousness, without minds to observe and comprehend, does it matter? Does a universe without observers have meaning? We might be the only beings in the cosmos capable of asking these questions, capable of understanding physics and mathematics, capable of creating art and music and literature. If we fail, if we destroy ourselves or stagnate and eventually fade away, we extinguish the only light of consciousness in an otherwise dark and uncaring universe. That's a heavy burden. It means every decision we make, every action we take as a species, has cosmic significance. It means the future of intelligence in the universe depends on us getting things right, and we're not doing great. Climate change threatens to destabilize our civilization. Nuclear weapons remain capable of ending human civilization in hours. Political divisions and conflicts continue unabated. We're still struggling with basic problems like poverty, disease, and inequality. Can we overcome these challenges and build a sustainable, spacefaring civilization? Or are we heading toward the great filter, the catastrophe that will end our story? Being trapped in our solar system, unable to leave, unable to spread to other stars, doesn't answer these questions. But it makes them more urgent. If we can't escape, if the solar system is our only home, then we need to make it work. We need to learn to live sustainably, to manage our resources, to resolve conflicts without war, to preserve Earth's biosphere while expanding into space. We need to become a civilization worthy of surviving, worthy of carrying the torch of consciousness forward. Because if we're alone, if there's no one else out there, then we're all there is. We're the universe's only hope of understanding itself, and that's worth fighting for. We're alone. Our solar system is an island in an ocean of darkness. The nearest other islands are so far away that we may never reach them. If there's life on those islands, intelligent life, civilizations, we may never meet them. We might detect their signals, we might communicate via radio across the light years. But we'll never shake hands, never sit down for a conversation, never share a meal or see each other's worlds. We're like villages on opposite sides of a vast ocean in an era before ships, able to see smoke from each other's fires, but unable to cross the distance. And that's assuming there are other villages. We don't know if we're alone in the universe, or if there are countless other civilizations out there. We've been searching for decades with radio telescopes, listening for signals from other intelligent species. We've heard nothing. Maybe they're out there, but too far away. Maybe they existed in the past, but are gone now. Maybe they'll exist in the future, but haven't arisen yet. Or maybe we're alone, the only intelligent life in the observable universe. That's a heavy thought. If we're alone, if Earth is the only place in the universe where life has developed intelligence and consciousness, then we bear an enormous responsibility. We're the universe's only way of knowing itself. We're the only beings capable of understanding the laws of physics, appreciating the beauty of a sunset, creating art and music and literature. If we destroy ourselves, if we fail to preserve what we have, we extinguish the only light of consciousness in an otherwise dark and uncaring cosmos. That makes our survival important, not just for us, but for the universe itself. And if we can't leave the solar system, if we're confined here forever, then this small corner of space becomes infinitely more precious. It's all we have. It's all we'll ever have. We need to take care of it. But maybe isolation isn't permanent. Maybe 1,000 years from now, 10,000 years from now, humanity will have advanced in ways we can't currently imagine. Maybe we'll discover new physics that allows faster-than-light travel. Maybe we'll develop the technology to build generation ships and send them to the stars, accepting that the journey will take centuries, but believing it's worth it. Maybe we'll find a way to upload consciousness and spread throughout the galaxy as digital beings, exploring and learning without the constraints of biology. Or maybe we'll do something completely different, something we can't even conceive of right now. History is full of problems that seemed insurmountable at the time, but were eventually solved. Humans once thought we'd never fly. The laws of physics seem to forbid it. We're too heavy. We don't have wings. But we figured it out. We understood the principles of lift and thrust. We built machines that could fly. Now we take it for granted. We once thought we'd never split the atom. It seemed impossible. Atoms are the fundamental building blocks of matter. How could you possibly break them apart? But we did. We unlocked nuclear energy, for better or worse. We once thought we'd never leave Earth's atmosphere. Space was an unreachable void. Now we have space stations orbiting our planet, satellites providing communication and navigation, rovers exploring Mars. Every generation faces challenges that seem impossible, and every generation finds ways to overcome them. Maybe interstellar travel is just the next impossible challenge waiting to be solved. Or maybe it's different. Maybe this is a fundamental limit, not a technological challenge, but a law of nature. Maybe the universe is structured in a way that keeps civilizations separated, prevents us from spreading too far, ensures that each star system remains isolated. If so, we need to accept it and make the best of what we have. The question, will we ever leave our solar system, doesn't have a clear answer. Not yet. Based on our current understanding of physics and our current technology, it's unlikely that humans will travel to other stars in the foreseeable future. The distances are too great, the energy requirements too high, the challenges too numerous. But unlikely is not the same as impossible. And humans have a remarkable ability to achieve the unlikely. We've done it before. We might do it again. If we do, if we somehow find a way to cross the vast emptiness between stars and establish ourselves around other suns, it will be one of the greatest achievements in human history. It will mark the transition from a single-planet species to a multi-star species. It will be a moment comparable to when life first crawled out of the oceans onto land, or when our ancestors first looked up at the stars and wondered what they were. But if we don't, if we remain in our solar system forever, that's not a failure. It's simply the reality of existing in a universe where the stars are far apart and the laws of physics impose limits. We can still thrive. We can still explore. We can still grow and learn and create. We can build a future worth living right here in this small corner of the cosmos. The solar system is our home. It might be our only home, and maybe that's enough. Tonight, we've confronted one of the most sobering truths about our existence. We are trapped, not by lack of imagination or ambition, but by the fundamental structure of the universe itself. The distances between stars are so vast that reaching them may forever remain beyond our grasp. Voyager 1, our fastest and most distant ambassador, has been traveling for nearly 50 years and won't truly leave the solar system for another 30,000 years. The energy required to send humans to another star exceeds our current capabilities by orders of magnitude. The challenges, radiation, navigation, life support, psychology, seem almost insurmountable. We've looked at the possibilities: fusion rockets, light sails, generation ships, uploading consciousness, and none of them offer easy answers. We've confronted the paradoxes, the incessant obsolescence problem, the question of what we mean when we talk about leaving the solar system, the philosophical questions about identity and purpose. And we've faced the possibility that we may be alone, isolated in our small corner of the universe, unable to reach the countless other worlds that orbit distant stars. But we've also seen that this isolation doesn't diminish us. The solar system is vast, rich with resources and mysteries. There's enough here to explore and utilize for millions of years. We could build a thriving civilization spread across multiple worlds without ever leaving our star's gravitational embrace. And perhaps that's our destiny. Not to conquer the galaxy, but to perfect our mastery of our own small domain, to transform the solar system into a garden, a place where life and intelligence can flourish, even if we never spread beyond it. The question isn't whether we'll leave the solar system. The question is whether we'll make the most of what we have here. Whether we'll preserve our world, expand carefully into space, build sustainably, think in timescales of centuries and millennia, rather than quarters and election cycles. Whether we'll be good stewards of this cosmic island that gave us birth. The stars will always be there, distant and beautiful, calling to us across the darkness. Maybe someday we'll answer that call. Maybe we'll find a way to bridge the impossible distances and walk on worlds that orbit other suns. But until that day, if it ever comes, we have work to do here. We have a solar system to explore, a civilization to build, a future to create. And in the end, that might be the most important journey of all. Not the journey to other stars, but the journey to become a species worthy of making that journey. A species that has learned to live sustainably, to solve its conflicts peacefully, to value knowledge and exploration over short-term gain. A species that looks up at the stars, not with desperation to escape, but with wonder at the universe we're part of. We may never leave our solar system, but we can make our solar system a place worth staying. Thanks for staying with me through this journey, across the boundaries of what's possible. The stars are far away, perhaps forever out of reach. But the journey of understanding, the quest to know our place in the cosmos, that journey has no limits. And it's a journey we can all take part in, right here, right now, from our small blue world, orbiting an ordinary star. The universe is vast. We are small. But we are here, thinking, questioning, wondering, and maybe that's enough.